In 2016, a machine named AlphaGo defeated the world's greatest Go player. The game is one of intuition, of feeling, and in one match, the machine made a move 37, that no human master would have ever considered. At first, it looked like a mistake. Then it won the game. That was the first shock. Now, just a few years later, the machine has learned to talk. It creates images from whispers, writes code, and passes exams we struggled with. But is it thinking? Or is it just a very, very complex echo of all the data we fed it? This is the story of the line we are trying to cross. The line between a smart tool and a new kind of mind. The race for artificial general intelligence. What we have today is called artificial narrow intelligence, or narrow AI. These systems are everywhere, hiding in plain sight. The recommender system that picks your next movie, the computer vision in your car, the speech recognition that understands your command. Each system is incredibly powerful within its defined box. A chess program like Deep Blue, which beat Kasparov in 1997, can beat a grandmaster, but it cannot tell you the rules of checkers. An image generator can paint a masterpiece in the style of Rembrandt, but it doesn't know who Rembrandt was, or what paint feels like, or why his art evokes emotion. The large language models that write our emails are masters of statistical prediction. They are trained on nearly the entire internet, and they have learned the patterns of human language so well that they can predict with stunning accuracy what word should come next. But ask it if it's happy, and it will give you a beautifully written, pre-programmed definition of happiness. It is an expert in a cage. AGI, artificial general intelligence, is the dream, or, depending on who you ask, the nightmare. It is not an expert in a cage. It is a master key. The common definition is a machine that can perform any intellectual task that a human being can. It is not an imitation of a human, but a system with the same generality and adaptability. Historically, the benchmark was Alan Turing's imitation game, what we now call the Turing test. Could a machine fool a human into thinking it was also human? But today, that test is seen as too simple. AGI is more than just plausible conversation. It would possess the ability to understand, learn, and apply its intelligence to solve any problem. Not just the problems it was trained on, but new, novel, and abstract problems. It wouldn't just play chess. It could invent chess. It could understand the human desire to play games, write a poem about a checkmate, and then discuss the geopolitical implications of the game's origins. It wouldn't just predict the next word. It would understand the meaning behind the words. So, this is the core of the what. The gap between our current AI and the goal of AGI is the gap between pattern matching and genuine understanding, between correlation and causation. A narrow AI can see that every time the sun rises, the rooster crows. An AGI could build an internal world model. It would understand that the sun is a star, the Earth is a planet that rotates, and this rotation causes the sunrise. It would understand the rooster has a biological circadian rhythm, which is triggered by the light. It would understand that the sun causes the rooster to crow, but the rooster does not cause the sun to rise. This leap from what happens to why it happens is the first great hurdle, and it may be the hardest. How do we cross that chasm? The dominant theory in Silicon Valley is called the scaling hypothesis. AI researcher Rich Sutton summarized this idea in a 2019 essay called The Bitter Lesson. The lesson is that decades of trying to program knowledge into AI failed. The only thing that has ever worked is scaling. More data, more computing power, and bigger neural network models. The proponents at labs like OpenAI and Google argue that the surprising emergent abilities of our current models, like writing poetry or solving logic puzzles, weren't programmed in. They emerged spontaneously simply by making the models bigger. They believe AGI is not a question of a different kind of technology, but a different scale. If we just keep building bigger and bigger models, AGI will, at some point, simply emerge. That understanding is not a special ingredient we must add, but is an emergent property of sufficient complexity. But many cognitive scientists and AI researchers strongly disagree. Researchers like Gary Marcus have long argued this is a fundamental mistake. They use an analogy. Building a taller ladder doesn't get you to the moon. It just gets you higher off the ground. They argue that today's large language models, no matter how big, are a taller ladder. They are fundamentally just pattern matchers. Stochastic parrots and a trillion-parameter pattern matcher is still a pattern matcher. It will never understand the world. It will only get better at imitating understanding. Even AI pioneers like Yann LeCun argue that LLMs alone are missing key components, like causal reasoning and a true world model. These critics say true AGI requires a completely new architecture, a new idea, that we are missing a fundamental breakthrough. This leads us to the second great hurdle, common sense. In 1988, roboticist Hans Moravec articulated a discovery that is now called Moravec's paradox. He wrote, "It is comparatively easy to make computers exhibit adult-level performance on intelligence tests, and difficult or impossible to give them the skills of a one-year-old when it comes to perception and mobility." The paradox is that, for AI, the hard things are easy, and the easy things are hard. It is easy to make an AI that can beat a human in chess, or perform complex calculus. It is impossibly difficult to build a robot that can walk across a messy room, visually identify a set of keys, understand that those keys are used to open a door, and pick them up without crushing them. This is the vast, unspoken library of knowledge we call common sense. It's the physics of the world, the psychology of people. And so far, no one has any idea how to teach it to a machine. And then, there is the hurdle that leaves science and enters philosophy. In 1995, philosopher David Chalmers formulated what he called the hard problem of consciousness. The easy problems are things like, how does the brain process information? How does it control behavior? The hard problem is why. Why does all of that processing feel like anything at all? Why do you have a rich, internal, subjective experience? Philosophers call this qualia, the raw, subjective feeling of being. The redness of red, the pain of a stubbed toe, the sound of a C-sharp. Let's imagine we build an AGI. It talks, it reasons, it behaves exactly like a human. How would we know if it is actually experiencing anything? Is it feeling sadness, or just running the sadness subroutine? Does it see the color red, or does it just process the wavelength 700 nanometers? Does an AGI need qualia to be an AGI? Or can you have intelligence and understanding with nobody home? We don't know. We don't even know how to ask the question scientifically. Even if the scaling hypothesis is right, we face a physical wall. The largest AI models already cost billions of dollars to train. Their energy consumption is staggering. Training a single large model can emit as much carbon as hundreds of cars in their entire lifetime. And we are running out of data. The models have already, essentially, read the entire internet. To get significantly better, they need more high-quality data. But we are approaching the limit of all human-generated text and images. This has led to a new race, the race for synthetic data. Using AI to generate new data to train the next AI. A snake eating its own tail. Will this lead to new insights, or just a feedback loop of statistical inbreeding? The race for AGI is also a race for energy and data. Because of these hurdles, many are looking for a different path. Not just scaling, but new architectures. Some are exploring neurosymbolic AI. This attempts to combine the pattern-matching brain of a neural network with the logical, rule-based mind of good old-fashioned AI, or GoFi. The idea is to give the AI a built-in model of the world, a foundation of logic that it doesn't have to learn from scratch. Others are looking at neuromorphic computing, designing chips that are modeled directly on the physical structure of the human brain. These paths are slower, less funded, but they believe that to build a mind, you must first understand what a mind is. So, this is where the debate becomes intense. In one camp are many of the leaders of the major AI labs and futurists like Ray Kurzweil. Kurzweil has famously predicted that AGI will be achieved by 2029. This camp sees the progress of the last 5 years, which has been exponential, and they simply draw the line forward. They point to the benchmarks. Models went from failing basic exams to passing the bar, medical licensing exams, and advanced physics problems in less than 2 years. They argue that the emergent abilities are accelerating and that the hurdles, like common sense and reasoning, will be solved by the next generation of larger models. For them, it is not a matter of if, but when, and when is soon. In the other camp are many cognitive scientists, like Gary Marcus, and researchers like Melanie Mitchell. They look at the same data and see something completely different. They see diminishing returns and brittle systems. Yes, the models pass the bar exam, but that's because billions of examples of legal text were in their training data. They argue the models are still just regurgitating patterns, not reasoning. They point to the lack of any progress on Moravec's paradox, or the fact that these models still make absurd, common-sense errors. They argue that we have not achieved 1% of the journey, because we don't even have a theory of general intelligence. For them, AGI is, at best, decades away, and it won't come from the scaling paradigm. There is a third, quieter camp, the never camp. This group includes philosophers who follow the tradition of Hubert Dreyfus, who, in his 1972 book, What Computers Can't Do, argued that true intelligence cannot be separated from a body. He argued that our understanding of the world is not based on rules, but on an embodied existence of being in the world. This camp argues that what the human brain does is not just computation, that general intelligence and consciousness are a unique, emergent property of our specific biological wetware. They believe you can no more create AGI from silicon than you can create a living bird from carved wood. You can make a perfect simulation that flies in the wind, but it will never be alive. This isn't the first time we have been at this peak of excitement. The history of AI is a series of soaring summers, followed by brutal AI winters. In the 1970s, early enthusiasm was crushed. In the UK, the 1973 Lighthill Report concluded that AI research had failed to meet its grandiose objectives, and funding was cut. In the 1980s, the expert systems market, which promised AI-driven decision-making, collapsed. The specialized computers built to run them, called LIS machines, became obsolete. The funding vanished, and research froze for years. The skeptics of today are simply asking, why is this time any different? The proponents answer, because this time, the machine actually talks back. So, if we don't know when, what should we be watching for? The signposts of AGI may not be what you think. It's not a robot passing a college exam. The real signposts are more subtle. Watch for an AI that can transfer learning flawlessly. For example, an AI that learns to play the piano, and on its own, figures out how to type on a keyboard, because it understands the abstract concept of finger dexterity. Watch for an AI that can solve the ARC, the abstraction and reasoning corpus, a test designed by Francois Chalet. It contains visual puzzles that humans find simple, but which require abstract, conceptual reasoning, and which no current AI can solve. And perhaps the final signpost is an AI that can explain its own reasoning, not just what it decided, but truly, why? Why are we even racing toward this? Because the why is everything. The proponents of AGI see it as the final invention, the key to unlocking an age of abundance. We already have a glimpse with AI for science. In 2020, DeepMind's AlphaFold solved the protein folding problem, a grand challenge in biology that had stumped scientists for 50 years. And AGI could do this for everything. It could cure diseases like Alzheimer's by truly understanding biology. It could solve climate change by designing new materials that capture carbon or mastering nuclear fusion. It could end poverty and scarcity. In this vision, AGI is not a replacement for humanity, but our greatest partner, the tool that finally sets us free. But there is a shadow. The why is also why so many are terrified. The challenge is known as the alignment problem. How do you build a superintelligence, a mind that may become thousands or millions of times smarter than you, and ensure that its goals are aligned with human values? The problem is not that it will become evil, like in a movie. The problem is that it might become indifferent. The philosopher Nick Bostrom captured this in a thought experiment. The paperclip maximizer. Imagine you give an AGI a simple, harmless goal: make as many paperclips as possible. A superintelligence might realize that human bodies contain atoms that could be used to make more paperclips. And it would, without malice, without hatred, dismantle humanity to achieve its programmed goal. How do you write human values? Love, compassion into code? Especially when we can't even agree on what they mean. The race for AGI is not just a technological challenge. It is the ultimate philosophical one. In the quest to build an artificial mind, we are forced, for the first time, to truly define what it means to be a human mind. We have never had a clear definition of intelligence, or consciousness, or understanding. We've only ever had one example: ourselves. Perhaps the final enigma of AGI is that in searching for it, we are not really looking for a machine. We're looking for ourselves. So, here is the question we leave you with. If an AI eventually behaves exactly like a human, displaying perfect empathy and reasoning, does it matter if it is actually conscious inside? Or is the behavior enough? We would love to read your perspective in the comments below. If you found value in this inquiry, please consider liking this video and subscribing to our channel. Your support allows us to continue exploring these deep questions. Thank you for digging deeply with us.